In digital pathology, retrieving images from a repository is useful for supporting diagnostic tasks, comparing the progression of a given patient against others, or even creating scientific illustrations. Unfortunately, the typical way a pathologist stores those images makes it difficult to index and search them according to the similarity. A possible solution for this problem is using content-based image retrieval systems. These are computational tools used to retrieve relevant images from a repository based on the visual content. CBIR systems have been used on the medical field, and the performance greatly varies according to the field of application. It tends to be low when the images from different subjects or categories have a subtle difference between them. This frequently occurs in nephropathology. For example, in kidney biopsies, depending on the type of the lesion of interest, the images from a healthy glomerulus may be just slightly different from the images of the lesion ones. Having this in mind, we initiated the development of PathoSpotter Search, a CBIR system designed to be part of the PathoSpotter project. This project is dedicated to creating tools and knowledge for aiding the diagnosis and facilitating other tasks in nephropathology, as annotation of structures in whole slide images and retrieval of similar cases based on images of glomeruli. To develop PathoSpotter Search, we used a typical CBIR architecture composed of a feature extractor followed by a similarity score calculator. First, the system will extract and organize a set of descriptors from the images. Those descriptors are typically a feature vector or embedding. The second task the system will perform is ranking the images according to a similarity score between the descriptors, usually computing the distance between the vectors and ordering them accordingly. The combination of a convolutional neural network with a neural network creates a convolutional neural network, which has proven to be successful architecture for several computer vision tasks, particularly image classification. This has motivated the use of convolutional networks as feature extractors for CBIR systems. We chose two well-known convolutional neural network architectures for performance tests in the systems. They were VGG16 and InceptionResNet, as they presented good results in several classification tasks. Going even further, we applied fine-tuning to VGG16 using the public ChemiaPath 916 dataset with 916 histopathology images of 20 different classes. We also evaluated a proprietary convolutional neural network used in a classifier for hypercellularity. For distance ranking, we also evaluated two functions to compute similarity score, cosine and Euclidean distances. We performed experiments to measure the performance of the system in two different contexts, both using the architecture described in the figure. In the first experiment, we evaluated the performance of the system using a dataset with different types of glomerular lesions. They are relatively easy to distinguish. In a second experiment, we evaluated the performance of the system using a dataset with variants of the hypercellularity lesion. The difference between images are even more delicate. In total, we assessed 8 CBIR configurations based on 4 feature extraction: VGG16, original and fine-tuning, inception and proprietary, and 2 similarity functions, cosine and Euclidean distance. Provided that the images of the datasets are grouped into classes, we assess the precision of each CBIR configuration. We counted the numbers of images correctly retrieving using all the images of the dataset as query images in each test. An image was considered as correctly retrieved if it belonged to the same class as the query image. For example, if the query image presented sclerosis, the K retrieved images must present sclerosis. The precision for each class was calculated, dividing the number of correct images retrieved by the total numbers of images in the class. The results of experiment 1 and 2 are available in Table 3 and 4, and Table 5 and 6 respectively. In Experiment 1, using images of different glomerular lesions, the VGG16 architecture yielded the best average precision, although its performance was inconsistent between classes. This same architecture also outperformed its counterparts in Experiment 2, in which the images tend to be more similar to each other since they are related to the same glomerular lesion. It can be noted that the average precision of Experiment 2 was greater than the ones from Experiment 1. That may indicate that both VGG and Inception were capable to compute better discriminant features for hypercellularity than for other lesions. It was somewhat a surprise that the feature structure of the proprietary classifier performed poorly when compared to the others. We initially hypothesized that the convolutional network of this classifier would be able to generate good discriminative features of the classes. Although the classifier yielded an accuracy above 18% for hypercellularity multi-class classification, it is clear that it is not generating features discriminative enough to yield a good performance for a generic CBIR system. Using the VGG16 without fine-tuning and cosine distance, we published the system as a cloud service, so it could be tested by pathologists of the PathoSpotter project. Although the performance is still below our 70% goal, the system received positive reviews for its usability and functionality, indicating its usefulness as a tool to aid pathologists in their daily tasks. The system operates as described in the figure. First, the pathologist indicates the folder with images of interest. Then, the system creates a database of the feature vectors of those images. Finally, the pathologist saves this database for reusing it to retrieve images from this repository. It is worthy to note that, to assure the confidentiality of the information, no image upload is required from the system to operate, as all the computation of the feature vectors is done locally. Then, the pathologist indicates the database of the feature vectors for the images of interest previously built. Then the user loads the query image and informs how many similar images the system must retrieve, and the system returns k images from higher to lower similarity scores. As far as we know, the PathoSpotter search is the first approach to build a CBR system specific for nephropathology images. We are investigating why using fine-tuning in VGG16 did not lead to a better performance for the system. It is also an open question why the proprietary convolutional network used in PathoSpotter classifier did not get higher results. Currently, we are improving the system performance to reach at least 70% of mean average precision by evaluating other feature extractors and analyzing feature sensitivity. We also are evaluating strategies to retrieve similar images based on segments or tiles of the query image. This was the presentation of the initial results of the PathoSpotter search system, a CBIR system for digital images of kidney biopsies. Thank you for watching.